Dear students, in previous lecture we discussed two-dimensional discrete random variable. In today's lecture we will discuss two-dimensional continuous random variable. We will discuss two-dimensional continuous random variable by virtue of an example as given here. The joint density function of two continuous random variables x and y is fxy equals to 2 by 3 into x plus 2y, where x and y both lie between 0 and 1 and fxy is 0 in all other cases. We have to find marginal density of x and y, that means individual density of x as well as individual density of y, as well as we have to prove that both these variables x and y are stochastically dependent. We will see how it can be proved. Then conditional density of x given y equals to y means px upon y, and then we have to use it to evaluate that particular value of probability px less than equals to half upon y equals to 1 by 2. Let's start the proceedings. With that, I would like to discuss one more thing. There may be involvement of some constant also in that function, joint PDF, joint density function, maybe 2 by 3 into k into x plus 2y, and you may be called to calculate the value of that unknown constant, say k or lambda, whatever it is. Then what you have to do? You have to solve double integral minus infinite to infinite limit for x and minus infinite to infinite limit for y, fxy dx dy equals to 1. So you have to assume that double integral for minus infinite to infinite limit for both x and y, and then fxy is to be integrated, and that double integral is to be put equals to 1, because that is nothing but sum of all probabilities of the source. Using that equality, substituting the double integral equals to 1, and by solving the double integral, that is by integrating, that unknown constant can be evaluated. Here no unknown constant is given. We are given with these three parts. We start with joint density function as given there, and we need to calculate marginal density, individual density, that is of x and y. Individual density of x is easy to get. Fxx is the symbol. Then we have to integrate that joint density fxy with respect to y. If we have to get marginal of x, integrate fxy with respect to y. If we have to get marginal of y, which we will see in next slide, then integrate fxy with respect to x. That is a contrast kind of thing. So here we have to find marginal of x. So we are integrating that joint PDF fxy with respect to y within minus infinite to infinite as theoretically prescribed limits. But here we can see that y is in between 0 and 1. So finally that is integrated between 0 and 1, because in other cases it is 0. And then fxy 2 by 3x plus 2y between 0 to 1, limits for y and x is to be treated as a constant, 2 by 3 as a constant taken outside. By integrating and taking limits 0 to 1 for y, finally it is 2 by 3 into x plus 1, and it is the case fxx, that is individual or marginal density of x, is 2 by 3x plus 1 when limit for x, as we know, 0 to 1 and 0 in other cases. Similarly, in next slide we will discuss marginal distribution function of y. Let's talk over that marginal distribution function of y. Fy, we have to integrate that joint density function fxy with respect to x now within minus infinite to infinite as limits suggested theoretically. Practically we know that x is lying between 0 and 1, so 0 to 1 limits are practically taken limits, and then fxy is 2 by 3x plus 2y with respect to x, y is to be taken as a constant while integrating, and then limits for x 0 to 1 are substituted. Finally a function of y is obtained as 1 by 3 into 1 plus 4y. When y is lying between 0 and 1, it is fyy, and 0 in other cases. So that is, we got fxx and fyy as marginal distribution function of x as well as of y here. Now if we multiply that fyy and fxx which we obtained in previous slide and then we check whether fxy, the joint density, is equals to product of fxx or fyy. We will easily find that product of this fyy along with that fxx is not equals to the given joint density fxy. That's why we have to say that x and y are stochastically dependent. If in any other problem you find that fxy is equals to, that is joint density is equals to product of marginal densities of x and y, then you will say that x and y are stochastically independent. But here x and y are stochastically dependent variables. Now we discuss part C of that problem, where we have to find conditional density of x for y equals to y, that is f x upon y, and symbolically capital X upon y is taken outside. If you don't take that x upon y outside, still it's okay. And we know that PA upon B, conditional formula is PA intersection B, and here it means fx intersection y means joint density fxy upon fy means fyy. So that is a simple formula for finding that conditional density of x for y equals to y. Divide joint density by marginal density of y, you will find that conditional density of x for y equals to y. If you have to find its reverse, that is if you wish to find conditional density of y for x equals to x, what you have to do? You have to divide joint density by fxx in that case, okay. But here that conditional density of x for y equals to y, that is joint density divided by marginal density of y, and we know that joint density of xy from the beginning it's given as 2 by 3 into x plus 2y, fyy which we calculated in final step of last slide as 1 by 3 into 1 plus 4y. If you simplify it, you will get 2 into x plus 2y upon 1 plus 4y, and it is conditional density of x, so limits are to be kept over x. That's why limit, as you can see, because y equals to y already occurred for this case, so limit are to be kept over x only between 0 to 1. There is conditional density of x given y equals to y, and apart from that 0 less than x less than 1, in all other cases that conditional density is to be 0. Now as it was given, we have to calculate one more part of it, part of C, that probability px less than equals to half upon y equals to 1 by 2 using that conditional density. How is possible? As y equals to 1 by 2, that is we have to use this form, you can see using form of fx upon y. So y is to be substituted particularly 1 by 2 in these two places, y equals to 1 by 2 here and there, and then x less than equals to half, that is actually written as minus infinite to half, but as per that restriction that x lying between 0 and 1, so x less than equals to half means 0 to half. So you can check it dx, so limit for x is 0 to half. We are integrating that conditional density for finding this probability. 0 to half limits taken for x, and y equals to 1 by 2 is substituted there, and that's about 2 into x plus 2 into y is 1 by 2, so 1 x plus 1 upon 1 plus 4 into y is half, so 4 into half is 2. You can check that. So it is simplified as 1 by 3 0 to half 2 into x plus 1 dx. If you integrate and substitute limit for x 0 to 1 by 2, finally that value is obtained as 5 by 12.